Well, we've just finished up with sampling distributions, and just as a quick refresher, so here is our original distribution. And if I do samples of size 25 and I want to plot the mean and I do this 10,000 times, I get this new distribution down here. And remember that it'll, as an unbiased estimator, will still be centered at the center. So mu of x bar down here, these are my x bars, will equal the mean of the original distribution, 16 and 16. All right, the standard deviation of my original distribution was 5. All right, my new distribution is 0.99. All right, so remember though, standard deviation of a sampling distribution is sigma over the square root of n. 5 divided by the square root of 25, so it's like 5 divided by 5, which is 1. 0.99 is really close. If I were to do this another 10,000 times, so we actually got a little further away and then got closer together, and do it 100,000 times. And now, so I've done this well over 100,000 times, my standard deviation is 1. Standard deviation of 1, so if I go mu plus or minus 1, so 16, that's my mean, plus or minus 1, 15 to 17, I would expect 68% of my means to be in that interval. Empirical rule, remember? 68% of the means from this sampling distribution are within one standard deviation of the true mean. 95% of the sample means that I have, 95% of my x bars, are going to be somewhere within 2 standard deviations. So being that my standard deviation is 1, that'd be from 14 up to 18. And that's an important thing, because now what we're going to do is we're going to scale this back and say, what if I only do one sample? What if I only do one sample for the mean? And I sample 100, let's sample 10 things. If the actual mean is 0.5 and the actual standard deviation is 10, and I sample 10, and I do that sample, I'm going to show you something. So this was the sample of data that came from that distribution. My actual mean was negative something there. Is it listed over here for me? No, it's not. So, the actual mean, is 5.654, and that's lower than the mean. All right, and that's interesting because there says I'll have to check that out. Anyways, and then I construct this confidence interval, this green line. This green line is a 95% confidence interval, and we're going to do that quickly, and we're going to figure out how to calculate those. But what I'm going to do is I'm going to use this interval to estimate where the mean actually is. And in this case, the actual mean, which I knew, is in that interval. Now, granted, the mean is negative. That's a negative, that's why. Negative 5.646, which is right there in the middle. You can see the lines at the end. And we can see that that interval barely captured the true mean. Now, in this case, we know the true mean, but we don't always know the true mean. And let's say instead of one interval, I'm going to do 10 intervals. So we'll recalculate. 10 intervals, and then we'll sample. Oh, change that to 0, 10, there we go. N is 10, sample, there we go. So now we've got these intervals, and we can see that this particular one includes the mean, but this one down here does not. So we happened to get one of the samples. Let's change this back. Means, there we go. Now, sample. That's better. It was doing proportions. We'll come back to proportions. This one down here went from negative 13 up to negative 0.778. It did not include the actual average of 0.5. What does that mean? That means that just by chance, I did a random selection and I got this interval that did not include the true mean. If I'm only constructing a 95% confidence interval, I would expect that if I were to do this process and do all these things, which we'll do shortly, and notice that each time I do this, it changes and shows you what the actual data was. Every time I do one of these, I'm going to calculate a new interval. You'll notice that all of the intervals are the same width because they're all 95% confidence intervals. What happens if I want to be more confident? If I want to be more confident, what will happen to that interval? What do you think? Look at that. They got wider. Just think of it like a fishing net. If I want to be more confident in catching a fish, I use a bigger net. So I'm going to recalculate that down to 95. But if I do this repeatedly, I'm going to expect that on average, about 95% of those intervals that I make will include the actual mean. All right. With any one interval, I would say I have a 95% confidence that the actual mean is in there. In this case, we know that it is because we can see that it is, but in most real life statistics, we don't know. So maybe we got that one. And then we go, oh, but how do we know? The answer is we don't. We have to rely that we're using proper methodology. I keep doing this. So if I were to do this 100 times, or 10 times, because it's 10 intervals, let's see. Well, let me do 100. Look at that. There's 100 of them. 1, 2, 3 are red. So we would expect on average about 95% of them to be green. In this case, it was 97. Do it again. There's 4. There's 5 that time. Ooh, 1, 2, 3, 4, 5, 6, 7, 8, 9 that time. So if we did this tens of thousands of times, 95% of these intervals would contain the true mean. I could do the same thing with proportions. If my actual pi is 0.7, we'll do a calculation of 100. Let's do a sample. It does the same thing. Look at how wide those intervals are. How can I make my interval narrower? How can I be more precise? Well, I could be less confident. If I'm less confident, I don't need a wide interval. See, they're not quite as narrow. Now, here though, you'll see that the intervals actually have different widths. And that's because proportions and how they do calculations for sigma is slightly different. All right, but if I increase my sample size to 100, look at that. My intervals are so much narrower now. More data. I reduce variability of the sampling distribution, which means I reduce variability, potential variability in my sample, which means I have a more precise answer. So now I'm going to go back up to 95% confidence and redo it. Now my intervals get a little bit wider, but they're still narrow because I used a much larger sample size. This idea is what's called confidence intervals. A confidence interval, which I will abbreviate CI oftentimes, is an estimate or a point estimate plus or minus a margin of error. Okay, and that margin of error is going to be calculated different ways. If I'm talking about estimating pi, okay, which is the same thing as p, if I want to estimate pi, I'm going to use p hat plus or minus z, and that's the same as from the z-score, times p q over n square rooted. Now, if I don't know p, how can I use p in my formula? Right here. Like, what if I don't know p? All right. The most common thing that we do is we say, well, what's my most conservative, least precise, like, if I have no idea what percentage or probability something's going to be, what's my most conservative estimate? And the answer is 50-50. So for p, I'd use 0.5, and for q, I'd use 0.5. All right, if I have an idea about what p might be, I'll use those numbers. But if I want to be just the most conservative estimate possible, I would use 0.5 and 0.5. All right, if I want to find mu with a confidence interval, I'm going to do an estimate for mu, which is x bar, because that's the average of a sample, plus or minus z times sigma over the square root of n. So margin of error, we'll see, margin of error is equal to a my standardized value, and this is z comes from the confidence interval. We'll do a couple of these and you'll see what I mean. And then times the standard deviation of the statistic. It's on your formula card where you can look it up. But basically, estimate plus or minus z times standard deviation of the statistic. Now, pretty soon, we're going to find out for mu when sigma is not known. What if we don't know sigma? What if we don't know sigma? Because it's a parameter. What if we don't know it? It will be x bar plus or minus t. I'll introduce you to the student's t distribution times s over the square root of n. political polls. Let's say that 47% of people approve of the current presidential situation. And then over here is plus or minus 3% is my margin of error. And usually that 3% is listed in the bottom corner. And they might even say that the margin of error is 3%. Oftentimes they will only say plus or minus 3%. So that means my confidence interval is 0.47 plus or minus 0.03, which is 0.44, comma, 0.50. All right, now we're going to interpret that we're going to interpret this in context. So you would say I am 95%, because this was a 95% confidence interval. We were, in this case, told that. I am 95% confident that the actual proportion of people, in this case, or voters, I'm 95% confident that the actual proportion of people who approve of the president is between 44% and 50%, or 0.44 and 0.5. All right, I'm 95% confident that the actual proportion of people who approve of the president is between those two numbers. I will never say there's a 95% chance that it is, because that is dealing with probability, not with a confidence interval. All right, if I were to repeat this process 10,000 times and do a confidence interval for each one of them, I would expect 95% of those confidence intervals to include the actual proportion, even though I don't know what it is. Now, it could be 0.440001, could be 0.499999. I don't know where it is in this interval. I do not have a higher confidence that's in the middle of the interval. Remember, because we looked at that applet. I just know that I'm 95% confident that it's in that interval somewhere. Conditions to use a confidence interval. Just like we did last chapter, we have to have these conditions, and the first one is SRS. Second one stands for independence. Third one is normality. And the last one said, I said we were eventually going to include it, but the answer, and that's sigma. So when we're doing this, you want to make sure all those four conditions hold true. What I want you to do is remember what those conditions are for a proportion. Write down how you know those are true to do a proportion problem. Write those in the reflection response and do that before you come to class. This is your introduction to confidence intervals.